Hello, bitizens of the internet, and welcome to Learnabit. In today's modern world, people around the globe live with more technology than at any point in human history. As a species, we are more interconnected than ever before via high-speed travel and the internet, and we have more immediate access to more knowledge than our ancestors did. At the fastest pace in history, we are advancing our knowledge of life, of the Earth, and of the fundamental ways in which our universe works. Most of these incredible advancements are due in large part to our understanding and application of science, and due to the millions of scientists around the world who have devoted their lives to the pursuit of knowledge. However, even in developed countries with comparatively excellent universal education systems, many people are still not really clear on what exactly science is, or why it should be trusted. Even many self-identified science lovers and advocates out there frequently misunderstand or aren't entirely sure what science is and how it works. In the United States, for example, only 52% of people could correctly identify what a hypothesis was on a 2019 Pew Research survey. So, if you had to explain what exactly science is to someone who had never heard of it, what would you say? How can you apply scientific concepts in your everyday life? And, maybe even more importantly, how do you differentiate between what is and what isn't science? Today, I want to give you the tools and the vocabulary to understand what exactly science is, so that everyone has a baseline understanding of how to talk about science. Let's get into it. So, it's a really big task to talk about the foundations of science. Therefore, we're going to break it down into two main halves. First, what is science? And second, let's talk about scientific literacy. Got it? Alright, so first, what is science? Let's break that part down into a few parts also. The history of science, common misconceptions about what science is, and finally, our modern definition. So, in order for us to understand the philosophy of science, let's take a look at a little bit of the scientific history. Crash Course has an amazing series on the history of science, which I'll link here, but let's just build a baseline understanding here. The word science comes from the Latin scientia, meaning knowledge, and entered English via Old French, meaning both knowledge and the collective body of human knowledge. However, the University of California, Berkeley's Understanding Science project, which much of this video is based on, states that science is both a body of knowledge and a process. So you can see from these definitions, science is not necessarily a new phenomenon. Almost every great ancient civilization, from ancient China to Mesopotamia, from Greece to Arabia, from ancient India to Egypt, and even far-flung regions like Mesoamerica, developed and practiced some early form of science and experimentation, which helped spur technological and conceptual advancement in those societies. Science in its modern form, meaning the modern scientific method, which we'll get into later, emerged in Europe beginning in the 17th century, during what is called the Age of Enlightenment. Thinkers began to question the world around them, and drew inspiration from, among other places, the writings of ancient Greek philosophers, such as Socrates, Plato, and Aristotle. These philosophers advocated discussing and challenging existing and emerging ideas, as well as using deductive reasoning and logic to make observations about the world around oneself. The Age of Enlightenment was due in large part to contributions from scholars from the Muslim world, who, in addition to a great number of their own advances, had also preserved translations of these ancient Greek and Roman philosophical and scientific writings that had been lost in Europe. They, and traders along the Indian Ocean and Silk Road, also helped bring other concepts and advancements from India, China, and Africa. So, the creation of modern science owes its existence to thinkers and writers from across the world, building on and challenging existing ideas and bodies of knowledge. you can still see this intercultural exchange of knowledge today in a broad number of fields such as science, philosophy, and mathematics. The suffix ology is Greek, meaning the study of. And algebra, for example, comes from the Arabic word al-jabr, which was spread to Europe by Muslim traders. And in modern times, although we call our modern system of numbers Arabic numerals, this system was actually first invented in India. Interestingly, the concept of the number 0 also originated in India. The numbering system was adapted and brought to Europe via Arab traders and travelers, where Europeans would further modify the numbering system into what we use today. So, it's clear from history that science is a global endeavor that booms whenever and wherever ideas are exchanged and challenged. All of those great ancient civilizations were focal points of trade and cultural exchange, and made significant technological and philosophical advancements. But we still haven't exactly pinpointed what modern science is, the type that we practice today. And I'm going to wager that many of you have some misconceptions about it. So I'm going to challenge you to pause the video right now and comment, or like a comment below, that says what you actually currently believe the definition of science is. Hit pause now. Done? Okay. Next, so that we can get to having a closer, clearer definition of science, it's important to dispel some misconceptions. What isn't science? Science, first and foremost, is not simply technology. Science can sometimes lead to technology, but a rocket ship or a computer by themselves aren't science. Second, science is not just mixing chemicals in test tubes and beakers to see what happens. That's not rigorous, careful, logic-driven experimentation. It's just playing around with chemicals until something happens. And finally, and perhaps most importantly, science does not start with an end in mind. We'll get into this a little bit later when we learn about pseudoscience, but there has been an unfortunate trend since at least the Enlightenment for people claiming to be scientists to start with an end assumption or goal in mind, and then attempt to find evidence to prove that goal. That's certainly not science, and we'll talk about that later. Anyhow, you've almost certainly seen all those ideas. They're everywhere in popular culture. The first things that show up when you Google the word science are images of colored liquids in test tubes and beakers, or rocket ships blasting off. But those are actually just applications of various scientific discoveries. After all, you can't really build a very good rocket ship without understanding scientific findings like gravity. Another important misconception some people have is that science is just limited to so-called hard science, or STEM subjects, an acronym meaning science, technology, engineering, and mathematics. These terms are often generally used to refer to natural sciences, chemistry, biology, and physics, as well as mathematics, while excluding other fields. However, there are many other types of science, such as the social sciences, subjects as diverse as economics, sociology, linguistics, and psychology. Those are all forms of science because they apply the scientific method via rigorous experimentation to deliver measurable and replicable results. Although their outcomes are sometimes less exact than the natural sciences, they still apply the same methods in research. Now we can finally discuss what science actually is. Science is a methodical way of thinking about the world and using logic to arrive at conclusions. Basically, according to UC Berkeley's Understanding Science, science is testing ideas with evidence. In school, you were probably at least briefly taught the scientific method. But what we don't often do a good job with is explaining that the method is actually a very simplified explanation of exactly what modern science is. Those steps are an easy guide to critical thinking, and they separate good science from junk science. You can think scientifically about many aspects of life, and the scientific method can work as a very clear, very basic scaffolding for logic. It's a bit too basic to fully explain the scientific process, but it's a good tool nonetheless. So let's quickly walk through the scientific method. There are many versions of the scientific method, so let's just use this very easy 6-step one that I've made. The first step is easy and it's something that you do all the time. Make an observation or ask a question. Then we take it a step further, do background research. We look to see if anyone has discovered anything that might help answer our question. Now we're ready for step 3, make a hypothesis. We'll get into this when we discuss scientific literacy, but a hypothesis is basically just an educated guess, a possible explanation for your question or observation. Fourth, you need to find a way to test your hypothesis, design and conduct an experiment. Fifth, you need to draw conclusions about the results of your experiment. Do the results support your hypothesis? Or do you need to adjust the hypothesis or experiment and try again? Finally, a good scientist records and reports all their results, positive and negative. And that's the scientific method. So you see, scientific thinking isn't just something you use in your science class. It can be used in many parts of our lives to draw conclusions based on logic. Alright, so now that you know how to work like a scientist, let's learn a little bit about how to think and talk a bit more like one. First, we'll examine 3 key words in science: hypothesis, law, and theory. Then we'll discuss 2 important concepts in scientific literacy: correlation versus causation, and avoiding biases. Finally, we'll use those concepts briefly to understand pseudoscience. Now, let's break down scientific literacy. So, first and foremost, there are 3 words that you need to understand to have a basic understanding of science. The first of these 3 is always the hypothesis. Like we said before, a hypothesis is, at the heart of it, a well-educated guess. A hypothesis is a potential explanation for your question or observation. It is not a theory, nor is it a law. There's a popular misconception that these 3 words are on a continuum. That once a hypothesis is found to be supported by evidence, it becomes a theory. And then when a theory is proven to be true, it becomes a law. However, this isn't true at all. A law is simply a description of a natural phenomenon. Often, a law can be a mathematical description, like the law of gravity. When we say Isaac Newton discovered gravity, what we actually mean to say is that he conducted experiments to determine the nature of gravity and observed a set of rules and constants. He then described the set of phenomena in his famous law of gravity. Newton's discoveries only described how gravity functions, but not why it functions that way. This is where theory comes into the picture. Theory as a word confuses a lot of people because of the difference in how we use it in everyday life versus how it is used in science. When we say theory in casual speech, we usually mean a guess. In science, that's no theory. That's a hypothesis. If you get nothing else from this video, just remember this. A theory is not a hypothesis, and a hypothesis is not a theory. Knowing that distinction is one of the most important bits of knowledge separating the scientifically literate from the illiterate. A scientific theory is a well-substantiated explanation for a phenomenon backed by a large body of hypotheses and experiments. Effectively, in science, a theory is as rock solid as a fact. The theory of gravity, after all, is just a theory. Okay, so I hear you asking, theory of gravity? A minute ago you just called it a law of gravity. And that's because, well, the law of gravity, or the mathematical description, is something entirely different from the theory of gravity, the explanation for why it works the way it does. Alright, so there's some basic vocabulary for your scientific arsenal. Now, how about some scientific concepts to make your experiments more rigorous and to help prevent errors? You may have heard the statement that correlation doesn't necessarily equal causation. Correlation is defined as a relationship between two things, while causation is defined as one action causing a particular outcome. Here are some hilarious examples to make this clearer. Global warming is correlated with a decline in the number of pirates worldwide. Is the decline of piracy responsible for global warming? Or how about this one? Use of Internet Explorer correlates with murders in the US. As usage of Internet Explorer as a browser declined, so did murder. Does this imply causation? Well, no, not at all. Logically, these things do not cause one another, so we can say they correlate, but there is no causal relationship. This is where avoiding bias comes into play. Human beings can naturally fall victim to our own desire of wanting to be right. Due to the way we are wired, we naturally fall for numerous biases, fallacies, and heuristics that we need to account for in science. There's the availability heuristic, or the tendency to make broad conclusions using only the information we currently have available. Let's see an obviously silly example. If your favorite color is green, and everyone in your family and friend group also loves the color green, you might jump to the assumption that green is the favorite color of everyone in the world. There's also the backfire effect, something you've probably noticed happen during arguments at family reunions. Your uncle makes a comment somewhat in favor of, let's say, political candidate A, and upon being challenged by your grandma, who supports political candidate B, your uncle suddenly doubles down on supporting candidate A. When one of our beliefs is challenged, we may decide to double down on our belief and hold it firmer than we did before. Most important, however, might be something called the confirmation bias, or a tendency to only believe or even look for information that confirms what we already believe. This desire to have the world conform to our beliefs is a large part of pseudoscience. At the beginning of the video, I showed a quote by social psychologist Carol Tavis that pseudoscience is popular because it confirms what we believe. Science is unpopular because it makes us question what we believe. Good science, like good art, often upsets our established ways of seeing the world. Pseudoscience is, by definition, something unscientific trying to pass as science. There are many, many, many examples of pseudoscience in our daily lives, and many forms of pseudoscience are clung onto dearly by their adherents. ThoughtCo has a great article online about how to identify science from pseudoscience, however. Obviously, go check it out afterwards. Link in the description. They recommend asking a few important questions to determine whether something is or is not pseudoscience. First, what is the purpose? Pseudoscience frequently starts experiments with an end goal of proving an ideology right. Good science begins with no such assumptions. Second, how are challenges dealt with? Are beliefs held dogmatically, and are challenges to those beliefs answered with hostility? Good science relies on and can withstand questioning and challenges. The truth can survive intense scrutiny on its own. Third, examine the research. This is where your newfound knowledge of biases comes in. Is the evidence rigorous and evolving? Or is the research merely prior assumptions being validated? Fourth and finally is something called falsifiability. Scientific theories have built-in conditions that would prove them false. If the sun is not the center of the solar system, for example, we would clearly be able to observe that the planet's orbits are traveling around some other point. If they revolved around Earth, the planets would move in a single circular direction around the night sky throughout the year. However, we can observe in Mars something called retrograde motion. Mars and the Earth orbit the Sun, but Mars takes longer to revolve. So, due to some interesting physics, for most of the year, Mars appears to circle the night sky in one particular direction, and then for a small portion of it, it appears to be moving the opposite way. The model of the solar system, with the sun at the center, is therefore not falsified by this evidence. Pseudoscience is unfalsifiable. Pseudoscience comes up with all sorts of bizarre explanations when holes are poked in the hypothesis. Bigfoot evaded you and covered all his tracks and is immortal, so we've never found a body. Things like that just seem too convenient. So, are you now a qualified expert, ready to take on the greatest minds in the world? Well, no, not exactly. But at least now you've got the foundations to begin to think more critically and more scientifically about your world. And now, you'll know how to read and sound more like a scientist, and how to spot the fake science that one particular family member keeps posting on Facebook. I hope you guys enjoyed this video, and thank you so much for watching Learnabit. Give this video a like and subscribe to this channel if you have not done so to learn a bit more.